Good morning. Can you hear me?
Good morning.
Thank you.
Yeah.
All right, just a reminder, if you'd please enable your video. Okay. It's got 9 people here today. All right. So let's go through what we were going through the other day. And we're looking now at quantum numbers, I think. That's the next topic. Anybody have any questions about the next test and how it's going to look or how it's going to be? Anybody have any doubts about what they're going to see here? Okay. I think you're all aware of the drill, that what's going to happen is you've got this practice test here, and the real test is going to look, well, pretty much the same as the practice test. It's going to be the same test, actually. So the best way to study for test 3 is to do this practice test multiple times, do it under the same conditions as you'd be doing the regular test, closed book. You are allowed to use a handheld calculator, though, so you can take advantage of that. But that would be the best method. And as I had told you the other day, there are questions here for the practice test. Every single question has a video. So if you're concerned about the wording or how to attack a question, I'd watch the video to show that. All right. So anybody have anything before I get started here? All right.
I have a quick question about
Yes, Joseph.
one of the credit quizzes, but that's more of a personal thing that we can
Okay.
talk about.
Why don't we talk about that after class, Joseph?
Okay. Yeah. Thank you.
Is it about the one we covered the other day, or is it about another one?
No, it's about a grade. It's
Oh, okay. All right, then we'll talk about that later.
Okay. Thank you.
Just want to download this, but it's not really. There it is. I see it's a bit slow this morning. There we go. Okay. All right, so we're going to first of all go through some atomic orbitals and quantum numbers. And one thing that we learned, well, we've already talked about, was the old model about the Bohr orbits. Let me get rid of this stuff over here. And the model that we're used to seeing, or have been used to seeing, that describes where electrons are in relation to the nucleus. All right, come on. Sorry, this is slow for some reason. Just trying to figure out what's going on, why this isn't working. Come on. All right, I'm going to close this program down and reopen it. that helps. For some reason, my tablet's not working here. My writing tablet. Something's going nuts with it for a second here. Sorry about this, folks. I don't know why this is giving me a problem right now. Just trying to figure out what's going on. Okay, now I think we're good. Okay. Still things are a bit slow. Okay. Let me see what the problem is. Sorry about this, folks. Let's try that again. It's all very frustrating. Something is slowing this down. I'm not sure exactly what it is. All right, I'll try this with my mouse instead for now. Okay. Oh, gee. It's all very frustrating. All right, things are getting better now. All right. So this is the model we're familiar with, where we've got a nucleus in the middle, and then we've got these energy levels. We talked about this in the context of energy levels where the electron could go to when it was excited and then come back down in and release photons as energy. And we talked about that last time. But this is not a particularly accurate model to describe exactly where electrons are. So what we need to look at is more like a more exact model. This is called the quantum mechanical model. And one of the things that we look at here is called the principal quantum number, which is n, which is actually these Bohr orbits that we just talked about, which gives a very, very rough idea of where the electron is as far as the energy level goes. And the n value can be 1, 2, 3, etc. We can talk about 3 kinds of orbitals. And the first one is the s orbital. And the s orbital is really just a sphere around the nucleus. And what that represents is the volume of space where we could expect to find that specific kind of electron. So it's just in a sphere around the nucleus. And when it's n equals 1, it's a small sphere. When it's n equals 2, it's a bigger sphere. N equals 3, it's a much bigger sphere. In the p orbitals, there's actually 3 of those. And the volume of space, I'm using my mouse here, so it's not nearly as effective as my tablet to draw with, but you can get the idea because you've seen this before. With the p orbitals, what we're looking at is kind of like a dumbbell shape volume of space around the nucleus where we can, where we can expect to find these electrons. Now, we talked about this in the context of electron configurations back when we were talking about module 12, if you remember. So if you remember what we were talking about there, let's say we're looking at 2p. And when we're talking about a 2p orbital, there were 3 energy levels. And these 3 energy levels, or 3 orbitals, match the 3 orbitals that I'm showing you here. So there's one for each of them. And then we have electrons in each of those, and we have a maximum of 2 electrons. And if you remember, when we fill the 2p, let's say we were just doing 4 electrons, we'd put 1 in each, and then the other one would go in the first one here. So we have to fill them, put 1 at a time in each of them, and then put 1 in here. And this would be effectively 2p4 is how it would look in the electron configuration. But the 2 here represents the n value, the Bohr orbit, if you will. So that's the n value right there. The other ways that we can make this more exact then, once we talk about these energy levels, is we can talk about which orbital they're in, and then, sorry, which subshell they're in, which would be the p subshell, and then which orbital the electron might happen to be in as well. So that would be represented by different kinds of values. The next one is called the angular momentum quantum number, which is L, which can have a value of 0, 1, or 2, all the way up to n minus 1. Now, these values represent a code, and they describe which subshell an electron might be in. So we're talking about the S, P, D, or F, and there's a corresponding number that goes with each of these letters. So for L equals 0, that's going to be S. For L equals 1, that's going to be P. For L equals 2, that's going to be D. For L equals 3, that's going to be F. So for this one, I'm going to have to close something down here. I don't know what it is that's causing my problems, but I'm going to close down Word here, see if that helps. Yeah, it looks like that might be using up some memory here. See if that helped. So that would be n equals 2. No, something is still not right here. See if I can close something else down. No. Let's close that down. See if that helps. Okay, so P here, that would be the L value, and in this case, L equals 1. That's in accordance with what we've got going on over here. So L equals 1, that's P. And then we need to be able to say, well, which one of these is the electron actually in? So let's say we're focusing on this specific electron here, but I'm circling here, or trying to circle. So that's where the electron is. Then we can talk about the next one, which is the magnetic quantum number, m sub L, which has a value from negative L up to positive L. Now, in the case of the p orbital, it means that the L value can then range from negative 1 up to positive 1. So what we can do is we can number these, as -1 up to +1. And that means that each of these can be assigned a number, but that number is dependent on the value of L, which we get from whatever the letter happens to be here for the subshell. So for this one, if I'm referring to this specific electron, then M sub L is equal to 0. All right, something is amiss here. I'm going to have to close down the share for a second so I can figure out what's slowing this computer down. Give me a second here, please. All right, hopefully will speed things up a bit here. So we've got our M sub L value here, which is representing which of these areas we're finding the specific electron that we're talking about. Oh, gosh, come on. Sorry, everything's going a bit nuts here. Waiting for it to calm down a bit. Okay. Sorry, it's all very frustrating today. Electronics are not being my friend right now. Okay. All right, I'm just going to go back to using my mouse for a little bit. So the M sub L value is equal to 0. And then whether the electron is up or down, we call this the spin. And in this instance, the spin is going to be M sub S, and this one is going to be +1/2. Now, if it's up, it's +1/2. If it's down, it's -1/2. So what that means is any given electron in an electron configuration can be assigned a unique set of 4 numbers, N, L, M sub L, and M sub S. And that will define, specifically, it's kind of like it's an electron address. And that's kind of what I've done up here. So we've got the 2p level, and we're specifically talking about this electron. N equals 2, and that matches the 2 here on the 2p. L equals 1, which matches the p, and that's from this little code over here. L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F. The M sub L is going to define which of these orbitals specifically it's in, and that one would be from -1, 0, and 1, so it goes from -L to +L. And then whether the electron is up or down is going to be determined by whether it's plus or minus a half. So that what we can do then is we can talk about valid and invalid sets. And that's going to be what the question on your test is going to be about. It's going to be looking at these different sets of quantum numbers and determining whether they're valid or invalid. So we can go back, we can take a look here at the allowed values in order to determine whether these sets are actually going to give a valid electron address or not. So in the case of the principal quantum number n, we can go from 1, 2, 3 up to infinity. As I told you, that's the Bohr orbit. It's the first number here in the electron configuration that tells you the n value. The L value can range only from 0 up to n minus 1. So what we know is that if n is, for example, 2, then the only allowed values for L would be 0 and 1. So what that means is that we can have 2s or we can have 2p, but we can't have 2d, for example. That would not be an allowed value. Now, the reason this makes sense is because let's say we were talking about the Bohr orbits. We've got n equals 1. The only possible thing you can have is a 1s. And that's because it's such a small orbit, because it's so close to the nucleus. For the 2, it's now possible to have s and p, so we can have 2s and 2p. For 3, we can have 3s, 3p, and 3d. So we can continue to add orbitals as subshells as the orbitals or the number of the n value gets bigger. And that's what we're noticing here. So the allowed values, again, for L would be 0, 1, if n is equal to 2, because we can go from L equals 0 up to n minus 1. If n is 2, then 2 minus 1 is 1, which means that L can only be 0 and 1, which means L can only be S and P. Does anybody have any questions about this? All right, I'm going to see, hopefully I've signed in here. I had trouble with this yesterday. Trying to make me sign in or something. All right, so I'm going to ask how you're doing with the understanding of this. I know you can see this, and that's okay. Okay, so there's our poll. I'll save that. Okay. So I'm going to launch this poll here. I want to see what your understanding of this is so far. If we're talking about let's be more clear. We're talking about the L values here. I'll give you another 10 seconds to vote. Remember, it's completely anonymous. I have no clue who's voting for what here. I don't have trouble with M. Okay, that's all right. We'll get to that in a second. Okay, that's all right, Joseph. At the present time, I'm really just asking about L. That's all right. All right, I'll end the poll here. So a lot of people only understand halfway. So I'm going to ask what questions people have in order to bring them to full understanding of what's going on here. So can anybody ask a question that will help here?
Well, maybe for the M, like I'm kind of confused about it.
The M?
Yeah.
Well, we haven't gotten to the M yet. I'm really just talking about the L at this point.
Negative L is bothering me. I don't know.
Okay, but we're not at M yet, right?
No, negative L. No, I said negative L.
Negative L. That's when we're talking about M. That's from negative L to plus L.
Okay.
Right. At the present time. Okay. Well, let's go back a little bit then. We'll go back a little bit. Does everybody understand what N is? What N represents? Well, we'll go with that.
Does N represent the number of values?
No, N just represents these orbits here, Michael.
Oh, okay.
The Bohr orbits, you know, where the electron is if we were just doing a very simplistic diagram of the atom.
Okay, thank you.
Okay. So actually, I won't even worry about that. Let's go back to the P value here. Or sorry, the L value. And L equals 1 being P. All right, so let's talk about the L value. Can anybody ask any specific questions about the L value that will help them? So what we're trying to do here is if we were given an electron configuration and a specific electron in that electron configuration, we want to be able to define its address, essentially. And we're using this set of 4 numbers in order to define its address. It's like if you were, you know, it's like if you've got a house, right? There's a city, and then there's a street, and then there's where it is in the street. Right? And that will define that house's address. You can find a house like that. Think of the city as being the entire thing, and then think of the street as being this set of orbitals, and then think of where it is in the street as being the specific orbital in the subshell, and then think of which side of the street we're talking about as being whether it's up or down. You know, you can look at it that way. You're just trying to zero in on a specific electron in the electron configuration. We already know where it is. So if it's a 2p electron in this specific orbital, then this set of 4 numbers will allow us to determine exactly where that electron is. So n equals 2 is from the 2 here in the 2p. The L equals 1 is for the p. And that goes by this code here: 0 for S, 1 for P, 2 for D, and 3 for F. So that's what we're at now with the the L value. Does anybody have any questions about the L value that could help them out here? I'm going to give you a little bit more information about this L value as well. Let's and its relationship to M sub L. I think that's what a lot of people are having trouble with, is the M sub L value here. I think I've sped things up a bit here enough that I can actually do something with it. Okay, it's good. All right, so if we look at the P orbital, let's look at the S orbital first. The S orbital is just one orbital. The P is going to be 3. The D is going to be 5. And the F is going to be 7. All right, we've talked about this back in module 12. Does anybody have any questions so far? 2, 3, 4, 5, 6, 7. Okay. So we've already talked for S. We know that the value is L equals 0. My computer is slowing down again, and I'm not sure exactly why it is. Okay. So L equals 0. And then we've got, that means that M sub L can only have a value of 0, because the value of M sub L is from negative L up to plus L. So if L is 0, then M sub L can only be 0, which is why there's only one s orbital, which would be marked with the number 0. For P, the value is L equals 1. So M sub L can be negative 1, 0, or 1, which means this will be negative 1, this will be 0, and this will be 1. For D, the value is L equals 2, which means that this can be negative 2, negative 1, 0, 1, or 2. This is why there's 5 orbitals in a D subshell. And for F, L equals 3, which means the values can go from negative 3 up to plus 3. That's why there's 7 orbitals in an F subshell. Okay, does anybody have any questions? That should clarify the L value for you. Let's see where you're at with that. So we're just talking about the L values here. What's your understanding of the L values like? Okay, that's a lot better right now. Okay, good. 5 more seconds. 4, 3, 2, 1. So that one's a lot better. It was the reverse pretty much a little while ago. So that's much better. Okay. Does anybody have any questions that they could ask to help them out here with the L values? All right, so that also helps with the M sub L values, because then the M sub L value for this one would be, if we were marking these as negative 1, 0, and 1, this specific electron would have an M sub L value of 0. This specific electron has an M sub L value of 1. And these two electrons have an M sub L value of negative 1, just because of where it is in the subshell, the P subshell. Does anybody have any questions? Okay, then the last thing is just which way the electron's pointing, or which side of the street is the house on. Is it on the left or the right? Is it pointing up or pointing down? M sub S plus a half means it's pointing up. M sub S minus a half means it's pointing down. Does anybody have any questions? All right, well, let's talk about valid and invalid sets then. So let's say you're given a four sets of quantum numbers here, and they all have 4 values in them. And we've got to see if these are going to be actually defining a valid electron address or not. So if you're looking at the first set here, n equals 3, is that an allowed value? Well, according to what I've got up here, the allowed values for n, which is the first quantum number, is 1, 2, 3, or anything else above that. It's an integer. And if you've got n equals 3, yeah, well, that's a valid number. So n equals 3 is valid. Now, L equals 3, is that valid? Well, if we look at what L is allowed to have, from what I said earlier, the allowed values for L are 0, 1, up to n minus 1. Now, if n equals 3, then allowed values would be 0, 1, or 2, which effectively means if you've got 3 as being your n value, then you're allowed to have 3s, 3p, or 3d, but you can't have 3f. And the reason for that is because, well, this would be the third energy level. There's not enough room to put an f orbital. We can have s, p's, and d's. We can't have f's. So when we look at this set of quantum numbers here, n equals 3 is okay. L equals 3 is not okay, because the maximum value for L that we can have if n equals 3 is 2. it can go from 0 up to 3 minus 1, which is 2. So 0 to 2, that makes this invalid. So that's why L is making this invalid. L can only be 0, 1, or 2. It can't be 3. And once you've found one invalid quantum number, the whole set is invalid. So that would mean this set is an invalid address. Does anybody have any questions about this?
So why can L only go up to 2 in this occasion?
Because the allowed values for L go from 0 up to n minus 1. So the value for L is actually defined by the n value you have at the beginning, Joseph. And we know that the n value is 3, which means L can only be a maximum of n minus 1, which is 2. Is that okay?
Yeah, that works for me. Thank you.
Okay. Understand though, it can't just be 2. It can be 0, 1, or 2. So that would mean that makes this whole set invalid if L equals 3. Any questions? Okay. Let's see the next one, n equals 4. So n equals 4, that is valid, that's fine, because n can be any integer, 1, 2, 3, 4, 5, whatever, so that's okay. L equals 3. Well, as we said earlier, L can be any value up to n minus 1. So n is 4, which means L can be a maximum of 3. L is 3 here, so that is valid. If we look at what that represents, according to what I've got up here, if L equals 3, that's the f orbital. So far what we're talking about is the 4f orbital. And again, my tablet's not working so well, so I'm just going to have to use my mouse here. 2, 3, 5, 6, 7. Okay. So we've got the 4f orbital, and the 4f can range from negative L to plus L. Where are we here? There we go. So negative L up to plus L. Now L, let's have a look. So 4 is n equals 4. F is L equals 3, which means that the m sub L is going to range from negative 3 up to positive 3, which explains why we've got 7 values there for the f orbital here. And what we're talking about specifically with this one, we can go a little bit further. The m sub L value is negative 1, which means what we're talking about is this specific orbital right here. All right, I'm going to stop there for a second. So up to this point, we've got something valid. Does anybody have any questions? So now we've zeroed in. Go ahead.
Oh, so the M doesn't help you figure out like the exact atom. It just helps you figure out like the type of atom.
No, all it's really doing is figuring out where the electron is in the electron configuration, Joseph. It's actually not defining any specific element. It could be any electron in any element, but it's going to be a specific electron in a specific electron configuration. We're just zeroing in on an address here. Is that okay?
Yeah, that helps. I thought the
Okay.
M was, yeah, thank you.
No, it's got nothing to do with the element, okay?
I have a question about the plus or minus 1/2.
Yes.
Could you just go over that real quick again? Like, how is it negative or how is it positive 1?
Well, if it's pointing up, it's positive. If it's pointing down, it's negative. This specific one is negative 1/2.
Okay, I see.
So it's just pointing down. So that would be the setup. That's what that electron. That would be the electron that this set specifically points to. Is this electron in the 4f level pointing downwards? If it was plus 1/2, it'd be pointing up, Code.
Okay, I see. Thank you.
Okay, so that tells you exactly what's going on here. Let's just do another poll here. We'll see how you're looking. Okay, so how do you feel about that specific problem? Remember, it's anonymous. I have no clue. I'll give you another 5 seconds here. 5, 4, 3, 2, 1. Okay. So most of you seem to understand what's going on with that. For the people who understand halfway, are there any questions that could help out here? Okay, let's do another example. So for C, n equals 2, that's allowed. Remember that n can be 1, 2, 3, 4, anything like that. The L value can be, in this case, it can go from anywhere from 0 up to n minus 1, which is going to be 1. 2 minus 1 is 1. So 0 or 1 would be allowed values for L. Now L is equal to 1, which is going to, I have to use my mouse here, which is going to be 2p. So 2 for the n value, L equals 1 is p. The m sub L can go from negative L to plus L, which is negative 1 to plus 1, which is going to be 3 possibilities here. The m sub L equals negative 1, that would be this specific one. And the m sub S is negative 1/2, would be an electron pointing downwards like that. So that would be that would represent that specific electron. Does anybody have any questions?
I have a question.
Karina.
The m sub L.
Yes.
It says that equals 0.
Oh, it does. You know what? I was looking at the wrong one.
You're good. I was just confused.
No, let's change that. The magic of technology. There we go. Thank you. There we go. I was looking at the one on the bottom. I've looked at the m sub L here. So yeah, so m sub L is 0. You're right, and the m sub S would be negative 1/2, which would mean it'd be pointing down. That would be that specific electron. Thank you very much. All right. Anybody got any questions? So those two that we just looked at, B and C, are both valid because we can actually define an electron with that set. In D, n equals 4, that's an allowed value. L can only be 0 up to 3, 0, 1, 2, or 3. It can't be negative 2, so that makes that invalid. So that's all you need. You need just one thing to make it invalid, and the whole thing's invalid. All right, does anybody have any questions? Well, let's take a look at the questions on the test. They're actually pretty easy, really. Once you know what you're doing, it really isn't that bad. I'm just opening up the practice test here. There's a quiz about this as well in the quantum numbers folder. Something is still slowing my computer down here. I'm not sure exactly what it is. So this is what the question looks like. It's in the quantum numbers section. We've got questions 7 through 10, I think. Yeah, 7 through 10. And you get a quantum number set, and you're asked to figure out if it's valid, and if it's invalid, why it might be invalid. Okay, so let's look at number 7 here. which answer best describes this set of quantum numbers? So n equals 3, that's allowed. L can be 0, 1, or 2, anything up to n minus 1, so that's allowed. M sub L can be any value from -2 up to +2, so that would be 1. So that would be allowed. And then M sub S is going to be +0.5. They can be plus or minus 0.5, so that one's allowed as well. So I would say that this is a valid set. So let's see exactly what electron this would be talking about, since it is valid, and you'll see why. So we've got, again, we've got the n value, which is 3. So I write down 3 here. And then we've got the 2, which means L equals 0 would be S, L equals 1 is P. I'll write this down here. Okay, so if L equals 2, that's going to be D. Now, the D value for L is equal to 2, which means that the M sub L values can go from -L to +L, which is -2 to +2. And the M sub L value is +1, which is this one here. And the M sub S value is +0.5. So that would be the representation. Okay, so I'll do a poll here, see how people are looking with it. Okay, so how do you feel about this question we just did? Five more seconds. 4, 3, 2, 1. Okay. So we've got 11 people understand, 2 people are halfway understanding. Those 2 people halfway understanding. Does anybody have any questions that could help here? Okay. All right, so looking at question 8, n equals 3, that's allowed. Now L can only be 0, 1, or 2. It can only go up from 0 up to n minus 1. So n minus 1 would be 3 minus 1, which is 2. L equals 3 is too big. That set is invalid because L is out of range. This one's valid. Anybody got any questions about this one? Okay. Let's look at number 9. So n equals 5, that's an allowed value. L can be anything from 0 up to n minus 1, which would be 4. So what we're looking at here is L equals 1. So that would be, so far, five for the n value. L equals 1, that's P, according to the codes down here. Now P is L equals 1, so we can have -1, 0, and 1 for the orbitals, so that's the 3 orbitals. M sub L is equal to 2, and that's going to be out of range. So that's how I know that this one is going to be invalid, because M sub L is out of range. Okay. How do you feel about this question? How do you feel about this question? I'll give you 5 seconds. 4, 3, 2, 1. All right, so as you can see, we got pretty much unanimous for the people who voted anyway. Okay, anybody got any questions? let's look at the next one. Which answer best describes the following? N equals -1. Well, N can't be anything 0 or 1 or -1 or anything like that. It can be 1 up to anything else, but it can't be -1. So that is invalid because N is out of range. Anybody got any questions? All right, so that's what you're going to have to need to be able to do, is just be able to know what allowed values are possible, what aren't possible. And I think you should be all right. Anybody have any last questions about this one? Okay. All right, let's look at some electron configurations of ions then. And for ions, I mean, we've already done electron configurations for regular compounds, but ions are a little bit different because they have fewer numbers or greater numbers of electrons than regular atoms or elements that we might be talking about. So I'm going to give you 2 examples here. The first one is calcium 2+. And calcium 2+, if you look at the number of electrons just regular garden variety calcium has, it's going to be 20. This is because of where it is on the periodic table. So let me see if I can pull up a periodic table here. Try and pull this up in a separate thing here. Actually, I had one in the in that test, didn't I? I didn't even realize it. Actually, I should just do that. I'll go back to that test. So as part of practice test 3, you do have access to a periodic table somewhere. You better have. Here it is. All right, so there's your periodic table. There's calcium right here. You can see it has an atomic number of 20, which means it has 20 electrons. So that's how I know it has 20. If it's 2+, what that indicates is that it's short 2 electrons. Because if you're looking at calcium, you're going to have 20 protons in the middle. So it's 20+, which means that if we were doing just a simple Bohr orbit situation, the way it would work out is we'd have 2 electrons in the middle. We'd have 8 electrons in the next row, which matches the periodic table, by the way. That's how I know it's 8. So 1, 2, and then 8. 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen's twice here, that's why there's 3 of them, but it's really 2. Then we've got 8 again. In the third row. And then we'll have 2 in the last row. So that's a total of 20. But if it's calcium 2+, what that indicates is that it's missing 2 electrons. These specifically leave, and that means that Ca2+ actually has 18 electrons. And how do I get that? Well, if we do the math on it, then we've got 20 protons still in the nucleus. If we take away 2 electrons, that's 20 minus 18, which is 2. So that's how I know that Ca2 plus is 18. Okay, I'm going to do a poll here, see how you're doing with it. All right, how do you feel about the Ca2 plus having 18 electrons? Okay, 5 seconds, 4, 3, 2, 1. All right, seems like everybody understands that. Anybody have any questions? All right. So if we're going to do the electron configuration, then what we can do is we can do the electron configuration for calcium, which is going to be 1s1, 1s2, 2s2. So remember, it's 1s2 for the top row here. 2s2 is for these 2 elements here, lithium and beryllium. Then it's going to be 2p6, which takes us 1, 2, 3, 4, 5, 6 in the p block. 3s, 2, 3p6, and then down here 4s2. That's for calcium. And calcium 2 plus would be removing these 2 electrons here. So that'd be 1s2, 2s2, 2p6, 3s2, 3p6. And if you add those up, it's going to be 18. 2 plus 2 plus 6 is 10, plus 2 is 12, plus 6 is 18. So that's where the 18 comes into play. Anybody have any questions so far about this? Now the thing is that means that calcium 2 plus actually has the same electron configuration as our friend neon. So because if we did, argon. As we did argon, that's 18. You can see it says 18 there. It would be 1s2, 2s2, 2p6, 3s2, 3p6. That would be argon. So what we can say is that Ca2 plus is isoelectronic with argon. Isoelectronic simply means the same number of electrons. That's what iso means, same electrons. Now that's not to say that Ca2 plus is argon. It isn't. The reason it isn't argon is because calcium 2 plus still has 20 protons in its nucleus, whereas argon only has 18 protons in its nucleus. So Ca2 plus is isoelectronic with argon. We know that these creatures here in the far row here, far right row, they're called the noble gases. And the reason that they're so noble is because they have a full octet in their outer shell, which makes them more stable. And this goes for these specific electron configurations as well. This is why calcium 2 plus actually is a favored thing, is because it is isoelectronic with a noble gas. So it confers this stability on calcium 2 plus that might not be conferred if it was a different kind of ion. So Ca2 plus is isoelectronic with argon, which is a noble gas. Does anybody have any questions? All right, let's see how you're doing so far with it. How are you doing so far with this topic? 5, 4, 3, 2, 1. Okay. So it seems like everybody's on the same page with this one. Anybody have any questions? Okay. I'll do one more example here. This is a negative ion that I'm going to do now, and that's for fluorine. Fluorine is F, which is -1. F minus. And that means that if we look at the number of protons we have for fluorine, we're looking at 9. So it's 9 plus in the middle. And remember looking at the other one here. Fluorine is over here, it's at number 9. That's how I know it's got 9 protons. Which means it needs 9 electrons. Which means we got 2 in the middle and then 7 on the outside. That would just be regular garden variety fluorine here. And then, whoops, there we go, that's 7. So now that has 7 electrons. But if I have another electron I add to it, that'll be F minus, which would be 9 protons for F. F minus still has 9 protons, but it's going to have, let's say there's 9 electrons for the F, it'll have 10 electrons. Which means 9 minus 10 is -1, which is where the charge comes from. So if the charge is -1, we have to add an electron. So what I'm doing is I'll do the electron configuration for F, which is 1s2, 2s2, 2p5. That gives 9. F minus is going to be 1s2, 2s2, 2p6, which is, again, isoelectronic with neon, which is a noble gas. All right, does anybody have any questions? All right. Well, let's take a look at the kinds of questions you're going to see here. Okay. So which diagram best describes the drawing of electron configuration of AR? So you can figure that out. I'm not going to worry about that question. That's one you can definitely do. That's just multiple choice. Okay, write the full electron configuration for SN plus. Probably should include something that has a number of unpaired electrons as well, but I'll look into that later. So SN plus. So what we do is we find tin. And tin is 50. And 50 electrons. SN plus is still 50 protons, but it's going to be 49 electrons. Remember, 50 minus 49 is going to be +1. That's what we're looking for here. Okay, so we do the electron configuration, be 1s2, 2s2, 2p6, 3s2, 3p6. That brings us down to argon, 4s2, and this is now the D block. There's 10 here, so 3d10. This is going to be 4p6. That brings us to krypton, 5s2 to bring us to Sr. Then we need D, let's see, it's 4d10. That'll take us to cadmium. And then 10 here, this is for 10. This would bring us to 4p2. Now, if it's Sn plus, it'll be exactly the same thing, except now it'll be, well, I'll just go ahead and write it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Sorry, that's 5, isn't it? It's 5p2. Sorry about that. So this would be 4p6, 5s2, 4d10, and then this would be 5p1. So it'd be one less electron. Now remember the energy levels. It goes 1, 2, 3, 4, 5 for the S. For the P, it starts at 2, 2, 3, 4. And for the D, it starts at 3, 3, 4, 5. And for Sn plus, we take away one electron from what we'd have if it was regular 10. And that would give us our electron configuration for the ion. Now, one other, in the quiz, not the test though, it looks like I probably should have had more questions about this in the test, but one of the questions that it asks, it would be about how many unpaired electrons Sn, let's say Sn plus might have. And what we would do is look only at this very last orbital, because all of these will have paired electrons up to that point. So all we have to do is really just do the 5p1 and see what we have. Now P is going to have three orbitals in it, and there's only one electron, so it'll look like that. So this would have one unpaired electron. If you were asked, let's say O minus, we'll say O minus, we'll do that. I'll give you another example here. If you're asked how many unpaired electrons O minus has, we could do the electron configuration for O, which is 1s2, 2s2, 2p4, that's for O. O minus would have one other electron there, 1s2, 2s2, 2p5 would be O minus. And if we were interested in the number of unpaired electrons, again, we just look at the 2p5 area. And 2p is going to have the three orbitals here, and 2p5, they'd be 1, 2, 3, 4, 5. So it would have one unpaired electron as well. So that's how you figure it out. All right, let's see how you're looking with the unpaired electrons. How are you feeling about unpaired electrons? Five, 4, 3, 2, 1. Okay, so anybody who answered, I don't know what the other three people are doing, but I don't know. Anyways, any questions? Okay. All right. I think let me look at the thing here. See what else we have to cover. Yeah, that's pretty much it for that. So what I'm going to do is on Monday, let's take a look at the schedule here. And we'll see how much time we've got left here. I think on Monday, I might have a chance to go back and look at some of those things that, you know, but I had asked you to look at for the videos. I did also put in the Zoom videos for last week, but I used ones from the previous semester that covered the same topic. So I think that might be useful to you. And I think you should go take a look at that. You don't have to, but you could, especially if you wanted a bit more information about things. But I'm getting the impression that we might get a chance to take a look at some of those things next Monday. But let's have a look at the syllabus and see what's due and when it's due. So we're looking for, let's see. Yeah, so test 3 is actually not due until 4/5. So we've got a little bit of time here. Yeah, I'll have time to go back and take a look at these on Monday and Tuesday of next week, which is the week of 3/29 here. And then, you know, we'll have plenty of time to go over the test as well. And yeah, I think we'll be all right. So Monday, I'll go over the stuff that I wasn't here to teach you. So you know, you'll get the advantage of that. Does anybody have any questions? All right. Well, then we'll leave it here for today. Whoops. Somebody has a question. Thank you. All right. No worries. Okay. Well, I'll see you all later on. If anybody wants to hang around, talk to me, they can.
I had the one question.
Yes, that's right, Joseph. Yeah. Well, so
I'll let him go first because mine's personal. He might have something.
Somebody else has something? Joseph, I'll have you wait for a second. Anybody else have a question? I guess not.
Thank you.
All right, no worries, Karina. Okay, it looks like it's just you and me, Joseph. All right.
Okay, so I took the entropy quiz last night.
Okay.
Entropy.
Enthalpy.
And enthalpy. Sorry. When I was taking it, I ran out of time in the middle of it, and I had already gone through and put the descriptor, the kilojoules over moles for everyone, and then I went back and changed the answer at the last minute, and I got the answer correct, but I deleted my space on accident.
Oh, okay.
I was wondering if I could get points for that, or I know the question said make sure you put a space in between, but I was literally at like 20 seconds on the clock, and I forgot to check that.
Okay, let me take a look. I'm going to stop the share for a second, Joseph.
No problem.
Okay, now this was the enthalpy credit quiz, right?
Yeah.
Okay. I'm just going to take a look at it. Okay. Let's see what you're talking about. Yeah. Yep. Now I'm going to give you 0.9 because the sig figs are wrong.
I'm okay with that. It's better than a 0.
All right.
Thank you.
Now, to get the sig figs, Joseph, to get the sig figs, it's all based on the smallest number of places past the decimal.
Yeah.
Okay.
Okay. Thank you.
From any of those values. All right. No worries.
Yeah.
Okay. Is there anything else?
No, that was just it. I just wanted to make sure I didn't get a 75 and have to retake it. Thank you.
No worries.
Have a nice day, and I'll see you
Joseph.
Monday.
Bye-bye.